Ladies and gentlemen, welcome to our YouTube channel, where we embark on an extraordinary journey of discovery through the mysteries of the universe. Join us as we seek answers to fascinating questions like, where does space begin? What is the universe made of? Will it ever end? How many stars can we see at night? What types of stars exist? We delve into the twinkling of stars, the lifespan of celestial bodies, the vastness of the universe, and the laws of physics. We contemplate our origins, the beginnings of life, and the possibility of extraterrestrial existence. We ponder what makes us uniquely human and why space remains silent. To continue sharing this captivating knowledge and inspiring awe and curiosity, we kindly ask for your support. By clicking the subscribe button, you empower our channel and help us bring these discoveries to a wider audience. Currently, 98% of people enjoy our videos without subscribing, but with your support, we can reach even more curious minds. Together, let's embark on a remarkable journey of exploration and unlock the secrets of our universe. Thank you for joining us, and let's begin this incredible adventure together. Will the universe ever end? The ultimate fate of the universe is a subject of ongoing scientific investigation and speculation. There are several theories about the potential outcomes for the universe, including possibilities for its eventual end. Here are a few scenarios that scientists have proposed. The Big Freeze, heat death. This scenario suggests that the universe will continue expanding indefinitely, causing galaxies to move away from each other at an increasing rate. Over an extremely long timescale, this expansion would lead to the dispersal of matter and energy. As a result, the universe would become cold, dark, and virtually devoid of usable energy. This stage is often referred to as the heat death of the universe. The Big Crunch. In this scenario, the universe's expansion would eventually reverse due to the gravitational pull of matter. The universe would contract, leading to a big crunch, where all matter and energy would collapse into a dense, hot singularity, possibly resulting in another Big Bang and a new cycle of the universe. The Big Rip. This hypothesis suggests that the expansion of the universe will accelerate to such an extent that it would overcome the gravitational forces holding galaxies, stars, and even atoms together. The accelerating expansion would eventually tear apart all structures, including galaxies, stars, planets, and ultimately atoms themselves. This hypothetical event is known as the Big Rip. It's important to note that these scenarios are based on our current understanding of the universe, which is subject to revision as new observations and theoretical developments emerge. Additionally, the timeline for these events, if they were to occur, is measured in billions or even trillions of years, making it far beyond the current human perspective. Ultimately, the fate of the universe is a complex and active area of scientific investigation, and the answer to whether the universe will ever end is still uncertain. How many stars can we see at night? The number of stars visible at night depends on various factors, including the observer's location, light pollution levels, atmospheric conditions, and individual eyesight. In ideal conditions, away from light pollution and with clear skies, a person with normal eyesight can see around 2,000 to 3,000 stars on a clear night. However, it's worth noting that this number can vary significantly. In areas with heavy light pollution, such as urban or densely populated regions, the number of visible stars can be drastically reduced, and only a few dozen or even fewer stars may be visible. In addition to the naked eye, using binoculars or a telescope can enhance the number of stars visible. With a telescope, it's possible to see significantly more stars, including fainter and more distant ones. Professional observatories and powerful telescopes used by astronomers can reveal millions or even billions of stars in the night sky, as well as other celestial objects such as galaxies, nebulae, and star clusters. It's important to remember that the number of stars visible to the naked eye is a small fraction of the estimated 100 billion to 400 billion stars in our own Milky Way galaxy, not to mention the billions of other galaxies in the observable universe. What types of stars are out there? There are several different types of stars in the universe, classified based on their size, temperature, and other characteristics. Here are some of the main types. Main sequence stars. The majority of stars, including our Sun, fall into this category. Main sequence stars are in a stable phase of their lives, where nuclear fusion reactions in their cores convert hydrogen into helium, releasing energy in the process. They come in various sizes and temperatures, ranging from small, cool red dwarfs to massive, hot blue giants. Red dwarfs. Red dwarfs are the most common type of star in the universe. They are relatively small and cool, with lower mass than the Sun. Red dwarfs have long lifetimes and are known for their faint, reddish appearance. Many red dwarfs are too dim to be visible to the naked eye. Yellow dwarfs. Our Sun is a yellow dwarf star. These stars are similar in size to red dwarfs but are hotter and brighter. Yellow dwarfs have a stable fusion of hydrogen in their cores and are capable of supporting life on nearby planets within the habitable zone. Blue giants and supergiants. Blue giants and supergiants are massive stars that are much hotter and brighter than the Sun. They have shorter lifetimes due to their high energy output and often end their lives as spectacular supernovae. White dwarfs. White dwarfs are remnants of stars that have exhausted their nuclear fuel. These dense stellar remnants are typically about the size of Earth but contain the mass of a Sun or more. They gradually cool over billions of years. Neutron stars and black holes. Neutron stars and black holes are the remnants of massive stars that have undergone supernova explosions. Neutron stars are incredibly dense, composed primarily of neutrons. Black holes have such intense gravitational forces that nothing, not even light, can escape from them. These are just a few examples of the various types of stars in the universe. The characteristics and life cycles of stars depend on factors such as their mass, temperature, and composition, leading to a diverse and fascinating array of stellar objects. Why do some stars appear to twinkle? The twinkling or scintillation of stars is caused by the Earth's atmosphere and its effects on the starlight as it passes through. The main factors contributing to this phenomenon are atmospheric turbulence and the refraction of light. Atmospheric turbulence. The Earth's atmosphere is not completely stable. It consists of different layers of air at varying temperatures and densities. These variations cause the light from stars to pass through regions of different refractive indices, leading to the bending or scattering of the light. As a result, the apparent position and intensity of the starlight change rapidly, causing the star to appear to twinkle. Refraction of light. When starlight enters the Earth's atmosphere, it encounters different layers of air with varying densities. The air acts as a medium through which the light waves travel, and as they pass through regions with different refractive indices, the direction of the light waves is altered. This refraction of starlight causes the apparent position of the star to shift slightly, resulting in the twinkling effect. The degree of twinkling can vary depending on atmospheric conditions and the altitude of the observer. Stars closer to the horizon may appear to twinkle more due to the longer path length of starlight through the atmosphere. While the twinkling of stars can be visually appealing, it poses challenges for astronomical observations from the ground. Astronomers often use techniques such as adaptive optics or space-based telescopes to overcome the blurring and distortion caused by atmospheric turbulence, allowing for clearer and more detailed observations of celestial objects. How long does a star live? The lifespan of a star depends on its mass. Generally, the more massive a star is, the shorter its lifespan. Here are the approximate lifetimes of stars based on their mass. Low-mass stars, 0.1 to 2 solar masses. Low-mass stars, such as red dwarfs, have the longest lifespans. They can burn their nuclear fuel, primarily hydrogen, very slowly. Red dwarfs, which are the most common type of star, can live for tens or even hundreds of billions of years. As they exhaust their fuel, they gradually cool and become white dwarfs. Medium-mass stars, 2 to 8 solar masses. Stars with masses between 2 and 8 times that of the Sun, like our Sun itself, have intermediate lifespans. They burn their nuclear fuel at a moderate rate and can live for about 10 billion years. Our Sun is currently middle-aged and estimated to have about 5 billion years left before it exhausts its hydrogen and evolves into a white dwarf. High-mass stars, greater than 8 solar masses. High-mass stars are much more massive and luminous than the Sun. They burn their fuel at a rapid rate and have relatively short lifespans. These stars can live for a few million to a few tens of millions of years. They eventually end their lives in spectacular supernova explosions, leaving behind remnants such as neutron stars or black holes. It's important to note that these timescales are rough estimates and can vary depending on various factors, such as the star's composition and its ability to fuse different elements in its core. The lifetimes of stars are crucial in shaping the evolution of galaxies and the distribution of different stellar populations throughout the universe. Is the universe infinite? The question of whether the universe is infinite or finite is still an open topic of scientific inquiry. While there is currently no conclusive evidence to definitively determine the true nature of the universe's size, scientists have proposed different possibilities. Infinite universe. One possibility is that the universe is infinite in extent. In this scenario, the universe would continue infinitely in all directions, with no boundary or edge. In an infinite universe, matter and structures would extend indefinitely, and there would be an infinite number of stars, galaxies, and other celestial objects. Finite universe. Alternatively, the universe could be finite in size. A finite universe would have a specific size or volume, and it could have different shapes, such as being shaped like a sphere or a torus. In a finite universe, there would be a limit to the number of stars, galaxies, and other objects, and one could potentially travel in a straight line and eventually return to their starting point. Observable universe. The observable universe refers to the portion of the universe that we can currently observe. Due to the finite speed of light and the expansion of the universe, there is a limit to how far we can see. The observable universe is estimated to have a radius of about 46 billion light-years, but beyond that, the light has not had enough time to reach us since the Big Bang. However, this does not necessarily imply that the overall universe is finite. It's important to note that the true nature of the universe's size is a topic of active research and investigation. Scientists use observations from cosmology, such as the cosmic microwave background radiation and the large-scale distribution of galaxies, to gain insights into the structure and size of the universe. Ongoing studies, technological advancements, and future discoveries may provide us with a more comprehensive understanding of the true size and nature of the universe. Are the laws of physics the same everywhere? The fundamental laws of physics, as we currently understand them, are believed to be the same everywhere in the observable universe. These laws describe the behavior of matter, energy, and the fundamental forces that govern their interactions. The principle that the laws of physics are universal is known as the principle of locality, or locality of natural laws. It is based on extensive experimental observations and theoretical consistency. Scientists have conducted experiments and made observations in various regions of the Earth and beyond, and the laws of physics have been found to hold true consistently. Moreover, the laws of physics have been tested and verified in a wide range of conditions and environments, both on Earth and in space. For example, the behavior of matter and energy, as described by the laws of physics, has been successfully tested in particle accelerators, astrophysical observations, and experiments conducted in microgravity environments. However, it is important to note that our understanding of the laws of physics is not complete, and there are still open questions and areas of active research. Theoretical frameworks such as quantum mechanics and general relativity provide a robust description of many physical phenomena, but they are not yet fully reconciled into a single, unified theory. Moreover, there are regions of the universe, such as inside black holes or during the earliest moments after the Big Bang, where our current understanding of physics breaks down, and new physics may be required to describe these extreme conditions. These are areas of active research and exploration in the field of theoretical physics. In summary, based on current knowledge and observations, the laws of physics are considered to be the same everywhere in the observable universe, although there are ongoing efforts to refine and expand our understanding of these fundamental laws. Where does space begin? The question of where space begins is not precisely defined and can vary depending on the context and perspective. However, there are a few commonly accepted boundaries that are used to define the beginning of space. Kármán line. The Kármán line is an internationally recognized boundary that is often considered the beginning of space. It is located approximately 100 kilometers, 62 miles, above sea level. This boundary is defined by the Fédération Aéronautique Internationale, FAI, and is based on the idea that at this altitude, the atmosphere becomes too thin for conventional aircraft to generate lift. Therefore, vehicles must rely on aerodynamic forces to stay airborne. Geocentric view. From a geocentric perspective, space is often considered to begin at the boundary of the Earth's atmosphere, which is typically defined as the exosphere. The exosphere gradually transitions into the emptiness of space as atmospheric particles become extremely sparse. Outer space treaties. Various international agreements and treaties have defined space in legal terms. For instance, the United Nations Outer Space Treaty, which was adopted in 1967, considers space to begin at the outer limit of Earth's atmosphere. However, the treaty does not provide a specific altitude or distance for this boundary. It's important to note that these boundaries are somewhat arbitrary and serve more as practical reference points than precise scientific definitions. The concept of space is a complex and multifaceted one, and its definition can vary depending on the context and purpose of the discussion. What is the universe made of? The universe is composed of various components, including matter and energy. Here are the main constituents of the universe. Ordinary matter. The most familiar form of matter is composed of atoms, which are made up of protons, neutrons, and electrons. Ordinary matter includes everything we can see, such as stars, planets, galaxies, and even ourselves. However, ordinary matter constitutes only a small fraction of the total mass-energy content of the universe, estimated to be around 5%. Dark matter. Dark matter is a mysterious form of matter that does not interact with light or other electromagnetic radiation, hence its name, dark. Its existence is inferred by its gravitational effects on visible matter and the structure of the universe. Dark matter is thought to make up about 27% of the universe's total mass energy. Its exact nature is still unknown, but it is believed to consist of as yet undetected particles. Dark energy. Dark energy is an even more enigmatic component of the universe. It is a form of energy that is responsible for the accelerated expansion of the universe. Dark energy accounts for approximately 68% of the total mass energy content of the universe. The nature of dark energy is not well understood, and its precise origin and composition remain speculative. Energy fields. The universe also contains various energy fields, such as electromagnetic fields, gravitational fields, and quantum fields. These fields permeate space and interact with matter and each other, influencing the behavior and properties of particles and objects. It's worth noting that the understanding of the universe's composition is based on current scientific knowledge, but ongoing research and discoveries may lead to further refinements and advancements in our understanding of these components. Why is space silent? Space is often referred to as silent because it lacks a medium for sound to propagate. Sound is a vibration that requires a medium, such as air, water, or solids, to travel from its source to our ears. In the vacuum of space, there is no air or any other substance to carry these sound waves. On Earth, when we hear sounds, it is because the vibrations produced by an object, like a musical instrument or a person speaking, travel through the air and reach our ears. Our eardrums detect these vibrations and convert them into electrical signals that our brain interprets as sound. In the vast emptiness of space, the absence of air or other matter means that sound waves have nothing to travel through. As a result, there is no medium to carry the vibrations and allow us to hear sounds in space. Astronauts working in space, for example, communicate using radios or other electronic devices rather than relying on sound waves. However, it's important to note that while space may be silent in terms of sound as we know it, it is not devoid of other forms of energy and waves. Space is filled with electromagnetic waves, such as light and radio waves, which can be detected and measured using specialized instruments and telescopes. These waves play a crucial role in our understanding of the universe and provide valuable information about celestial objects and events. How old is our universe? According to current scientific understanding, the age of the universe is approximately 13.8 billion years. This estimate is based on observations of the cosmic microwave background radiation, the afterglow of the Big Bang, and measurements of the rate of expansion of the universe. The concept of the Big Bang theory is central to our understanding of the universe's age. It suggests that the universe originated from an extremely hot and dense state around 13.8 billion years ago. As the universe expanded, it cooled down, allowing matter and energy to form and eventually give rise to galaxies, stars, and other celestial structures. The age of the universe is determined through a variety of observational techniques. One method involves studying the cosmic microwave background radiation, which is the oldest light in the universe, dating back to when the universe was only about 380,000 years old. By analyzing the characteristics of this radiation, scientists can estimate the age of the universe. Additionally, measurements of the rate of expansion of the universe, known as the Hubble constant, contribute to the determination of the universe's age. By studying the distances and velocities of distant galaxies, astronomers can estimate how long it took for the universe to expand to its current state. It's important to note that while the estimated age of the universe is currently around 13.8 billion years, refinements in measurement techniques and ongoing research may lead to slight adjustments to this value in the future. Nonetheless, the age of 13.8 billion years represents the best estimate based on current scientific knowledge. What is the biggest danger in space? Space presents several potential dangers to human exploration and space missions. Here are some of the biggest risks and challenges. Vacuum and lack of oxygen. The vacuum of space lacks breathable air and oxygen necessary for human survival. Exposure to the vacuum of space without proper protection can lead to rapid decompression, causing severe injuries or death. Therefore, spacesuits or enclosed spacecraft are essential to maintain a habitable environment for astronauts. Microgravity and musculoskeletal health. Extended exposure to microgravity in space can have detrimental effects on the human body. Astronauts may experience muscle and bone loss, cardiovascular changes, and a weakened immune system. Countermeasures such as exercise programs and advanced medical techniques are employed to mitigate these risks. Radiation exposure. Space is filled with various forms of radiation, including cosmic rays and solar particle events. Astronauts and spacecraft are exposed to higher levels of radiation compared to what we experience on Earth. Long-term exposure to radiation can increase the risk of cancer, damage DNA, and have other harmful effects. Shielding, monitoring, and radiation protection measures are crucial for astronauts' safety. Orbital debris. The presence of space debris, including defunct satellites, spent rocket stages, and fragments from past missions, poses a significant threat to spacecraft and satellites in orbit. Collisions with debris can cause catastrophic damage, and the amount of debris continues to increase. Efforts to track and mitigate space debris are ongoing to minimize the risks. Launch and re-entry risks. The launch and re-entry phases of space missions involve high velocities and intense forces. Malfunctions or failures during these critical stages can lead to launch failures, explosions, or accidents during re-entry. These risks require careful engineering, redundant systems, and rigorous safety protocols. Isolation and psychological challenges. Long-duration space missions, such as those to the Moon or Mars, involve extended periods of isolation and confinement. Astronauts may face psychological challenges like monotony, stress, and social isolation. Maintaining mental well-being through support systems, communication with mission control, and psychological support is essential. Technology and system failures. Spacecraft and systems are complex and subject to technical failures. Malfunctions in life support systems, power systems, guidance systems, or other critical components can jeopardize missions and astronauts' safety. Stringent engineering, redundancy, and thorough testing are essential to minimize the risk of system failures. Is it cold in space? In space, temperatures can vary significantly depending on various factors. However, in general, space is considered extremely cold. In the vacuum of space, there is no air or matter to conduct heat, so the transfer of heat by conduction or convection, as we experience on Earth, is not possible. Instead, heat can only be transferred through radiation, which is a much slower process. The temperature of space is primarily influenced by the balance between incoming radiation from nearby stars, including the Sun, and outgoing radiation from celestial bodies and objects in space. In the regions far away from stars, where radiation is minimal, temperatures can drop to extremely low levels. For example, in the empty space between galaxies, temperatures can approach absolute zero, which is approximately -273.15 degrees Celsius, -459.67 degrees Fahrenheit. In our own solar system, temperatures can vary significantly depending on proximity to the Sun, but in deep space, away from any significant heat source, temperatures can reach as low as a few degrees above absolute zero. However, it's worth noting that while space itself is very cold, objects in space can experience significant temperature variations depending on factors like their proximity to a star, the presence of an atmosphere, or their surface properties. For instance, objects that are exposed to direct sunlight can become extremely hot, while those in shadow or away from sunlight can become extremely cold. It's crucial for spacecraft and space suits to be designed to withstand these extreme temperature variations and provide proper insulation and temperature control for the safety and functionality of astronauts and equipment in space. How hot is the Moon? The surface temperatures on the Moon can vary significantly depending on the lunar day and night cycle. During the lunar day, when the Sun is shining on a specific region, temperatures can become quite high. However, during the lunar night, temperatures drop dramatically. On the lunar surface, temperatures can range from extremely hot to extremely cold. During the lunar day, temperatures can reach highs of around 127 degrees Celsius, 261 degrees Fahrenheit, in sunlit areas. This is because the Moon has no atmosphere to regulate heat and no significant protection from the Sun's intense radiation. On the other hand, during the lunar night, temperatures can plummet to lows of around -173 degrees Celsius, -280 degrees Fahrenheit, in shadowed regions. The lack of an atmosphere means there is no insulation to retain heat, resulting in rapid heat loss into space. These extreme temperature variations on the Moon pose challenges for lunar exploration missions and the design of spacecraft and equipment. To protect astronauts and equipment from these temperature extremes, insulation, heating, and cooling systems are implemented to ensure their safety and functionality. Can a star turn into a planet? No, a star cannot directly transform into a planet. Stars and planets are formed through different processes and have distinct characteristics. Stars are massive, luminous objects primarily composed of hydrogen and helium gas. They generate energy through nuclear fusion in their cores, where hydrogen atoms combine to form helium, releasing vast amounts of energy in the process. This fusion process is what makes stars shine. On the other hand, planets are much smaller and do not generate energy through nuclear fusion. Planets form through the gradual accumulation of gas, dust, and other materials in a protoplanetary disk around a young star. Over time, these materials clump together to form planets as they orbit the central star. While stars and planets can form from the same cloud of gas and dust, their formation processes diverge. The material in the protoplanetary disk becomes planets, while the central region with sufficient mass and density undergoes gravitational collapse, leading to the formation of a star. However, it's worth noting that there are rare scenarios where a star and a planet can have a somewhat interconnected existence. In binary star systems, for example, a star and a planet can orbit each other. Additionally, there are instances where a star can be orbited by objects called brown dwarfs, which are sometimes referred to as failed stars, because they lack sufficient mass for sustained nuclear fusion. These objects have properties that blur the line between planets and stars. In summary, while stars and planets are distinct celestial objects formed through different processes, there can be instances where they coexist in a system or where objects exhibit properties that bridge the gap between the two. Does sound travel faster in space? No, sound does not travel in the traditional sense in the vacuum of space. Sound requires a medium, such as air, water, or solids, to propagate. In the absence of a medium, like in the vacuum of space, there is no medium for sound waves to travel through, and thus, sound cannot propagate. In space, the most common method of communication between astronauts, spacecraft, and mission control is through radio waves or other forms of electromagnetic waves. These waves can travel through the vacuum of space and are used for transmitting and receiving information. It's important to note that while sound cannot travel in the vacuum of space, there are other types of waves, such as electromagnetic waves, example, light and radio waves, that can propagate through space and carry energy and information. These waves travel at the speed of light and can be detected and measured using specialized instruments and telescopes. Will the universe ever end? The ultimate fate of the universe is a topic of ongoing scientific investigation and speculation. Based on current understanding, there are a few possible scenarios for the future of the universe. The Big Freeze, heat death if the expansion of the universe continues to accelerate. As suggested by observations of dark energy, it could lead to the Big Freeze. In this scenario, the universe will continue expanding at an increasing rate, causing galaxies to move farther apart. Over an extremely long timescale, stars will exhaust their fuel, galaxies will fade away, and the universe will become dark and cold. Eventually, it is theorized that even black holes would evaporate through Hawking radiation, leaving only a sea of particles scattered across vast emptiness. The Big Crunch, if the expansion of the universe were to slow down and reverse due to the gravitational pull of matter, a scenario known as the Big Crunch could occur. In this case, the universe would eventually stop expanding and start contracting. Galaxies, stars, and other cosmic structures would be drawn closer together until they eventually collapse into a singularity, similar to the Big Bang. The ultimate outcome of a Big Crunch scenario is still a subject of scientific debate and is dependent on the exact properties of the universe. The Big Rip, in some theories, it is speculated that the expansion of the universe could continue to accelerate at an even faster rate, leading to a scenario called the Big Rip. In this scenario, the accelerated expansion would become so powerful that it would eventually tear apart galaxies, stars, planets, and even atomic and subatomic structures. This would result in a universe where all matter is pulled apart and destroyed. It's important to note that these scenarios are based on current scientific understanding and theoretical models. The fate of the universe is still a subject of active research, and future discoveries and advancements in our understanding of fundamental physics may lead to new insights and possible revisions to these scenarios. By the way, I want to take a moment to express my gratitude. I put a tremendous amount of effort into creating these videos for you. If you've found this content valuable and enjoyable, I kindly ask you to consider subscribing to my channel. Your subscription shows your support and serves as an encouragement for me to keep producing quality videos. I genuinely appreciate your support, and together, let's build an amazing community. So, don't forget to hit that subscribe button and let's embark on this journey together. Thank you for being a part of this and for making it all worthwhile.